to the very well-known episode where his colleagues at the studio di Padova, the University of Padova, where Galileo was at that time, wouldn't put their eyes in the telescope to see that, in fact, there were sunspots. There were very well-known sunspots, okay? They wouldn't put their eyes in the telescope because it had been proven by finally by Aristotle, that there couldn't be any element of corruption in the world beyond the moon, in the superlunar moon. And this is, I mean, the attitude of our colleagues have been exactly the same. So that's why, I mean, it's for me, that I happen to know a little bit of this history. I've studied it. It is appalling to see how it's been really reproduced, relived, in a way.
No, I think
Larry
was first.
Dr. Preparata, I understood from speaking to you a little bit earlier that you came out of particle physics. You came out of really the standard school of this thing, and yet you're looking at cold fusion because you see something here that is you're getting at something with respect to the whole standard model, the whole QED, QCD model. Can you explain that a little bit further, what you're seeing here?
Well, I mean, thank you for asking me. It's true that my interest in cold fusion really came from a previous experience, which goes back to my thesis, PhD thesis, back in '64, on the question of elementary particle, what was then called elementary particle physics, which later has become fundamental particle physics, if you want, and it has been synthesized in this great achievement of the human mind, which is called the Standard Model. Now the question is, we have seen so many of these results, you know, the electroweak interaction, the color interaction, the quarks. Everybody, you know, knows the quark, and most people know that the quark really pose a very great problem to the human mind. This is, you know, in this atomistic idea that you can chop off, you can, you know, break everything in smaller pieces. And this has been a tremendously successful line of research. We have come finally when we are hitting this particle which are called the hadrons, of which the protons and the neutrons is one example, but there's so many. We are hit a point where somehow the constituents, the quarks, that are deemed to be, you know, the constituent of this system, cannot be separated in any way from the container, you know, the hadron. And this, of course, I mean, the idea of parts and whole at this point becomes very confused, because in other words, the whole doesn't seem to be able to exist without its parts, and its parts without the whole. So this process of analysis, which has been extremely successful in breaking up the matter in smaller and smaller constituents, then stopped there. For me, this was really the obsession of my life, to try and understand how this was possible. And out of the obsession of my life, I realized I developed an idea of what the ground state, what the vacuum would be, in a system where there is a very strong interaction among the field, you know, the so-called gluons. Okay? So I think I believe I've given a solution of this problem back in '85, which has been totally neglected by the community because it was not conducive to another, to the ideology of modern physics, of modern high-energy physics, which has led to the SSC. I don't want, I don't want to attack the SSC here, but I only want to say that this ideology has given a tremendous price onto going to the structure of matter at smaller and smaller space-time distances, rather than trying to understand how these little objects that are quarks really live together and make a whole, which has very peculiar properties. In any case, this is not important, very important to say, but what is important to say that this experience and this solution of the problem gave me a good idea that condensed matter could be, under certain conditions, very similar to the ground state, to the vacuum of QCD. Okay, I cannot explain you exactly why this is so, but this is a true statement. So therefore, I developed an analysis of this ground state in terms of macroscopic quantum field theory. It's exactly the notion which gave me the possibility of understanding quark confinement. This is called quark confinement, the fact that quark has confined with the atom. And I was able, to understand a certain number of things, from the free electron laser to water as a kind of a free electric dipole laser, something like this. So when the Fleischmann and Pons announcement came, after a little bit of skepticism, because I really didn't know really what was, but after I learned from the paper of Fleischmann and the reports from friends who were sitting at the conference of Fleischmann at CERN and so on, I learned what this was really about. I could immediately relate this to the work I had already done and found out it made sense. In fact, with my friends Tullio Bressani and Emilio Del Giudice, we published in the month of May 1989, essentially less than a month and a half after Fleischmann and Pons' announcement, we published a paper in Nuovo Cimento, which is the Journal of Italian Physical Society, which had the title Towards an Understanding of Cold Nuclear Fusion and so on and so forth. It contains essentially the idea, differently from Peter Hagelstein, I didn't have any reason to change my idea up to this point. Okay? And, this is still rudimentary, but I think those ideas, that paper contained the basic ideas that would make a piece of magic would make it back to the realm of scientific rationality. And this is so, and to see that people were legislating, my colleagues were legislating against, like Hermann Feschbach and the other people, against this thing just on the basis of an incomplete and finally incorrect use of the laws of nature, really made me mad, because that showed that these people, of course, Hermann Feschbach is old, he's not able to learn, or less able to learn things. No. I mean, no. This is something that I'm going to subject to. I mean, this is something very grave and sad. That you see that, that the more you're advanced, the more things you know, the least easy for you is to incorporate new ideas. And that's a tragedy of a scientist. That's why people should leave, should not, I mean, people, this kind of society tends to believe more the senior people. I don't say that they shouldn't be believed. I'm only saying that there's this tragedy in the approach of the human mind to the new, to the emerging, okay? And that's what it is. That you essentially you cannot be able to tune in. You are not able anymore to tune in to new things. And unfortunately, society takes people with Nobel Prize, for example, who usually is rather old, who's been a scientist much more lucky than anybody else, who have had one good idea in his life, and they think they're going to have two. It's impossible. And it's impossible. So, I mean, this society gives a tremendous amount of weight to the advice and to the opinion of Nobel Prizes. And I think the chance that the Nobel Prize, who was right once, is able to be right twice, is just zero. They should rather give other people the chance. And then, and then, of course, my plea here is for a total openness, no authoritarianism in science. Everybody who thinks that an idea has to come to the fore. Of course, he has to be shot down if he's wrong. I mean, in fact, this creates a tremendous amount of moral tension in the people who are scientists, in order to be able to judge by themselves, for themselves, whether something is right or wrong, whether something is in agreement with the facts or not. Of course, it's much easier to say, what does the DOE say? What does MIT? MIT is the greatest school. What does MIT say? Wrong. Okay, fine, let's go. Very easy. But very much against the science itself. So I think, I don't know whether I have given an answer to your question, but true, my interest in cold fusion was really a corollary of work that was essentially occupied the better part of my scientific life. And I think I'm glad that these two things came together.